Hello, and welcome to, I guess, what we're calling unscripted, unscheduled, organized chaos, where you hang out with me and I talk about whatever, which is sometimes math, and sometimes I read stories, and sometimes we don't know. So if you're new here, welcome. I'm new here too, so we're both figuring this out. But usually I have tea, and none of this is high dopamine content, which I think I'm going to say a lot every single time, maybe, just in case anyone's new. And yeah, we kind of just talk, hang out, drink tea. You may notice that I have one braid at the moment. It's because I'm trying to make sure my hair doesn't get into the microphone. So yeah. So today I am going to talk about math because I did a bit of exploration this week. Not that much, but enough to just hop on, share, maybe chat about it. Ooh, chat. Kind of like a fireside chat, right? Have you ever heard of those? Or maybe a campfire talk. That would be better. The best conversations happen around a campfire, especially, and the best music happens around a campfire. When you have all your friends and some old guy, like your grandpa, has a guitar, or someone else's grandpa, and they're just playing the guitar, singing old songs. Best thing ever. Anyway, back to here. Okay, so math. Last week, or 2 weeks ago, I don't remember at this point, I started reading the book Measurement by Paul Lockhart. The part that I have read, I have made a video about, so I will either link it in the description or try to put it up here in the box if I figure out how to do that. And we only got through like the first chapter, essentially, the introduction and a chapter. And in that book, the author, Paul Lockhart, he leaves some questions in bold so that the reader can answer them. So you don't have to go back and listen to that to follow along with what I'm saying. But if you do want to hear the story, the video's there of me reading it, not just, you don't have to go read it yourself if you don't want to. So one of the questions, the very first question in bold in that book is, where is the center of an equilateral triangle? And so I was thinking about this question. And at first I was like, I don't know where to start. Like sometimes you just get a question, and especially when you're new to trying to figure out math or trying to answer questions, it's like, where do I begin? Well, when I was in high school, I had a great calculus teacher. And one of the things he always said is, remember the phrase, what do I know? Anytime you come across something new or something where you don't know where to start, ask yourself, what do I know? So, by the way, this applies not just to math, this applies to all of life. And funny story, the reason that I remember this is that I actually didn't remember it, but I found a Google document in my email that had listed like all the catchphrases and little things that my teacher had said for us to remember. We also had vocabulary words, which was fun. Anyway, I found it written there, and I was like, wow, I am so glad I found that, because that's what I'm going to do right now with this question. Where is the center of an equilateral triangle? So what do I know? I know that all sides of an equilateral triangle are equal. I know that all angles of an equilateral triangle are equal. I know that the angles of any triangle on, let's say, like 2D plane, right, the angles are going to add up to 180 degrees. And great, okay, what else do I know? I know that I can draw lines, I know that, let's say, well, okay, first back to all sides and angles being equal. That's kind of about symmetries, right? So a triangle has certain symmetries. So if we cut an equilateral triangle in half, and one side is going to be the same as the other, right? It has that certain symmetry. It also has the symmetry that if you rotate it around its center, right, then anywhere, if you so wait, what's 180 divided by 3? Is it like 60? I think it's 60, right? So if I rotate a triangle by 0 degrees, that's the identity symmetry, and it's going to remain a triangle. If I rotate it by 30 degrees, it's also going to maintain a symmetry because it's going to look like the same triangle. Like if I have a triangular table and I rotate it by 30 degrees or by 60 degrees. No, I did this wrong, not 30 degrees. If I rotate it by 60 degrees, there we go, or by 120 degrees, or by 180 degrees, or by 0 degrees, if you come back into the room, you're not going to notice that the table has been rotated. If I rotate it any other degree, right, like if I rotate it by 15 degrees, 30 degrees, when you leave and then you come back into the room, you're going to notice that the triangle table has shifted, right? So there are certain symmetries in the triangle. And I find that point kind of interesting because maybe that's important to answering the question, where is the center of an equilateral triangle? Well, the center is, in my head, I feel like it has to do something with the radius of a circle. Like the center of the triangle up to one of the vertexes is that length is going to be the radius of a circle by which you can, I don't know. So hold on. So I was thinking about it on paper, and I realized that I did not have the great artistic talent of drawing a realistic equilateral triangle every time I tried to draw a triangle, or at the minimum that if I wanted to do that, I would need a ruler. And I decided to instead use the internet or technology. I decided to use GeoGebra, which I actually used in geometry when I was in college. And so I opened GeoGebra and I started making some equilateral triangles, and I started just playing with them, and I made a bunch of lines on the triangle. And here's the thing. What I'm about to say is that, like, I found an answer to this question, but it's not a proof. And so you can clearly see that I have to work on this, and that's okay. So if you're watching this video and you've answered this question, don't tell me the answer yet. I'm going to go try figure it out still. I'm just telling you what I'm trying and what I'm exploring and where my ideas are coming from. And if you haven't answered this question before, where is the center of an equilateral triangle? Like in a not superficial proof sort of way, like in a not formal proof sort of way, then try to answer it. We'll see if we come up with the same answer once I figure this out eventually. So when I was using GeoGebra, I ended up drawing all these lines, which I guess we could call bisectors, which is where it goes from the vertex, it splits the angle in half, so it's going to be exactly 30 degrees of an angle on one side and 30 degrees of an angle on the other side, and all the way up to this midpoint right over here. And I drew that from all 3 vertexes. And I noticed when I found the length of the different segments, what happened was that this part of the line, which was from the vertex to the center, was about 2/3 of the line, and this part of the line, which was from the midpoint of a side to the center was 1/3. And it was the same for every single one of these lines. So like this is 2/3 of the line, this is 1/3. This is 2/3 of the line, this is 1/3. And so my idea is that maybe I can answer the question, where is the center of an equilateral triangle, by that ratio, that it's like 2/3 of the distance of the bisector from the vertex, or 1/3 of distance of the bisector from that line, from like the midpoint of the line. I guess the vertex makes more sense of a definition, but maybe that's where the center is. Is that really a proof? No. Do I need to think more? Yes. Do I think it has something to do with symmetries? Yes. And that's probably more important than my 2/3 or 1/3. But I'm sure that if I figure out more symmetries, then I'll have a better reason for why it seems to be that every equilateral triangle has its center in where, from the vertex of a bisector, the distance is 2/3 of the line to the center. Like, regardless of how long the actual line is, whatever it is, it's going to be 2/3 of that length from the vertex if you want to get to the center. And so, yeah. One of these days, I need to show you the actual GeoGebra thing I was playing with and do that, but today we're just talking because that's what I want to do. And along this topic of symmetry, I started listening to this audiobook, which is called Love and Math, which is by Edward Frankel. And I've gotten to, I think, about chapter 3. And I have to say, it's so cool. Like, I was listening to it, and I could just understand and even be excited about all these concepts that I once learned in in college, that at first didn't make sense to me, or at least didn't make sense why we were using them. For example, in abstract algebra, which was one of the hardest classes I think I took in, why do I keep saying high school? In college. I went to college. Abstract algebra was one of the hardest classes I took in college. And we learned about all these different things like groups and rings, and it felt so extremely abstract that I didn't get it. However, in this book, Love and Math, one of the first chapters talks about symmetries and uses the concept of symmetries in order to get to this concept of groups and why it's important, and how we can have groups even outside of symmetries. And so, do I remember all of it to tell you all of it? Maybe not. However, I want to say that it really sparked my curiosity. So, what Edward Frankel was talking about, I might have said his name wrong. We hope not, but he's Russian, so his name's like Edward Vladimirovich Frankel. The middle name, the middle part sounds Russian, and I don't know how to say the other two with a Russian accent. So, well, anyway, Edward might be like Edzik. I have a relative named Edzik. Anyway. Okay. Breathe. It is night. It is raining. We are cozy with tea inside, talking about math. Okay. So, let's talk about symmetries. One of the questions that Frankel talks about in his book is a circle, like we take a circle and we take a square, and we ask, what is more symmetrical, the circle or the square? And he specifically talks about a circle table and a square table in order to help us imagine it. That's kind of why I was using the table analogy when I was talking about the triangle earlier. So, for some reason, that question I could answer by myself. I was like, the circle. And then it's like, why? Why the circle? Well, because, no matter how much you turn a circle, you can turn it by any degree, any fraction of a degree, it's still symmetrical. I'm like, you can flip it and fold it in half from any possible line. You don't have to choose a specific line. As long as your line crosses through the center of the circle, like, you have an infinite number of ways you can fold it, and it remains symmetrical. It's like it has an infinite number of symmetries, right? Because what is a circle? A circle is the set of all points that are equidistant from one point on like a 2D plane. And a square, on the other hand, has about 4 symmetries. So you can rotate the square by its center. What is it? If we have a total of 360 degrees, right? Then, geez, do I remember how degrees work? Okay, so 360 degrees, right? Half of 360 is what? 15 plus 3 is 18. Oh, right, 180. Duh. So we have 300 degrees. 180 is half of that. And 60? No. What's half of 180? 90. Goodness, I really haven't done this in a while, have I? I really need to, review. Anyway, if we, right, because the square has 90-degree angles. Right. A right angle is 90 degrees. And a square, Okay, so we have a square table. If I spin the square table 90 degrees while you have left a room, when you come back, you will have no idea if I spun the table or not. If I spin the square table 180 degrees or 270 degrees or 360 degrees or 0 degrees, right? Each of those times, it's a symmetry. The square remains the same, right? You're not gonna, what is a symmetry? I feel like he explains that. What is a symmetry? A symmetry is when the object itself still looks the same despite having undergone a transformation. Is that how we define a symmetry? Like some transformation as in reflection, rotation, translation. Oh, it's coming back to me. Right. So, I guess we're specifically talking about rotation right now for a circle and a square. And the whole idea of something like groups was connected to there's this set of rotations that can happen. Oh my gosh, it's coming back to me. I see the blackboard in my head of me sitting in class and us talking about this now in geometry and possibly in abstract algebra, but maybe not. So we have a set of rotations in which the symmetry is maintained. So I forgot if the set becomes labeled an S, and if rotation was labeled an R, and I feel like at some point translation was labeled a T. But so we have R1, which is going to be a rotation by 90 degrees for the square. We have R2, which is a rotation by 180 degrees of a square. We have R3, which is going to be the rotation of 270 degrees by the square, and we have R4, which is going to be the rotation by 360, right? And 306, or is R1 0? Well, so the 360 rotation is the same as the rotation of R0 by 0 degrees. And so that becomes like the identity, essentially. So like you have the 4 actual angle rotations, and then you have the identity. And you can combine these different rotations. So like you can take a rotation of R1 plus a rotation of R2, right? So that's going to be a 90-degree rotation plus a 180-degree rotation, which is going to give us R3, which is the 270-degree rotation. But then the interesting thing is that some rotations are going to essentially cancel out the previous one. So if I take a rotation of R1, which is 90 degrees, if I add a rotation of R3, which is 270 degrees, now we're back to the identity, which is 0, which means that R3 is the inverse of R1, and R1 is the inverse of R3. And so now we have the idea of the inverse, which I believe was S prime or R prime. I'm forgetting the notation specifically, but I'm definitely willing to learn more about this and look this up later, just not right now. So we have an identity, we have a set of rotations which maintain symmetry, and we have like a set of symmetries, and we have an inverse in which every single symmetry or rotation has its particular inverse. And so like the inverse of R2 would be R2, because 180 plus 180 for a square gets us back to 0. And now the thing is, right, this whole thing of how 180 plus 180 equals 0, we could add 180 plus 180 plus 180 plus 180 plus 180, right? And we can keep adding, and we can get like a super huge number. And however, we would still end up within one of the 3 R's. We would, no matter how many, rotations we add, whether we add 90 degrees, 270 degrees, 180, 360, and however many multiples of that we add, we're always going to end up back in one of these 4 rotations. And that is clock arithmetic and modular arithmetic. And I love it because I learned about that one in cryptology. And that was such a fun class, because think about clock arithmetic and modular arithmetic is just absolutely mind-blowing and also so easy to explain to a kid. But the reason it's mind-blowing is because it's the math that you're like, that you can easily prove to someone math isn't what you learn in school. And why do I say that? Because when we learn math in school, or we're taught math in school, we're given all the memorization, and we're told 2 plus 2 is 4. And we're told, 12 plus 10 is 22. But it's not. It all depends on context. 2 plus 2 does not have to be 4. Now, don't go all 1984 on me. If you know what I'm referencing, it's a book by George Orwell. I don't mean that, okay? Just to be clear. So, read that also in high school. Great book. Had a great teacher with that book too. Anyway, modular arithmetic. 2 plus 2 does not have to be 4. So think about a clock. This is the best way to explain this. So we have a clock, and we have a 12-hour clock, imagine. And so let's say that it's 1 in the morning. So it's 1 a.m. So our clock is pointing out the number 1. So then let's say that 13 hours had passed. So 1 plus 13 would technically be 14, right? But we don't have a 14 on this clock. We only have 12. So when we take that 1 and we add that 13, what we actually get is 2. That 1 plus 13 equals 2, and it is the most valid statement. And so if we imagine not our normal clock of 12 hours, but we imagine a clock that has like 3 hours, let's say it just has 1, 2, and 3, then 2 plus 2 would equal 1, because we would have 2, right? We would add 2, so we'd go to 3, and then we'd go to 1, because there's no 4. And so 2 plus 2 equals 1 in modular arithmetic with a base of 4, right? The base is how many hours we're putting on the clock, is a completely valid statement. And boom. Math has nothing to do with memorization. It has nothing to do with what you were taught in school about memorizing stuff. It's all about the context. There's different maths in which what you were told to memorize no longer stands true. And that's why the goal isn't memorization, but it's understanding. And it's, learning how to work with the different concepts. It's not even about numbers. It doesn't have to be. Anyway, I think modular arithmetic is so cool. And I love explaining that. And I once explained it to an 11-year-old and her face was like, like, it was the best face I had ever seen. So, I'm just saying, she totally got it too. Like, she was 11 and she could do clock and modular arithmetic, right? And if we take clock and modular arithmetic and we take prime numbers, suddenly we have a good basis of like cryptography, like encryption and decryption, which keeps all of our passwords safe online. And isn't that just amazing? Like, come on, it's amazing. Math is so cool. Anyway, you can see that the more I start talking about things, the more I remember and the more I'm like, oh my gosh, like all of this is connected. Because we started talking about symmetries. The funny thing is, we started talking about symmetries. I was learning about that in my geometry class. We got to some small realm of like groups, which is having a set of the symmetries plus an identity plus an inverse. I think there was a fourth quantity or concept. I don't remember off the top of my head. I will have to research that and get back to it. But that was something I learned in abstract algebra, which in its own self, the symmetries and the groups and the modular arithmetic, now that was related to cryptography. Now I took those as 3 individual classes, and they're all connected in this one very moment thing that I'm thinking about, which is so cool. And I wish I'd learned it together because they're so connected. Like, imagine if I had learned about symmetries as the step up before the concept of groups in general, because I didn't get it. I needed the more concrete example of these symmetries and sets of symmetries, and then expand upon that and be like, okay, it doesn't only have to be things that are symmetrical. Now, beyond this, I cannot explain right now because I don't remember it off the top of my head. But did I understand it when I heard it? Yes. And am I going to go back to it? I really hope so. Because, as I said, I thought abstract algebra was one of my hardest classes, one of them. Except for also, I think, something like advanced calc or something, one of those. And in this very current moment, I am so curious about groups. and I want to know about them. And from what I understand, groups and symmetries are essentially what allowed physicists to know that there are quarks. So this now goes back to physics, right? So like physicists deal with the real world and like the nuances of the numbers and quantities and all those things. And math doesn't. Math takes the simpler things, takes the perfect circle, takes the perfect square, takes the perfect symmetry. And even though there are symmetries in real life, like a butterfly or a cup or something else, in math, we work with the perfect ones because in real life, none of them are actually really perfect. And so, what was I talking about? So, I don't remember what I was just talking about. I know that you can like click 5 seconds backwards and tell me what I was just talking about, but I can't do that while I'm filming this. So, what was I just talking about? Symmetries, butterflies. Goodness. Okay, well, math, physics. So, from what I understand, in physics, right, we have all these different atomic particles, and like the smaller you get, the more pieces there are. So we have like the atom, and then the atom has the nucleus and the protons and the electrons. And then within the protons and the electrons, we have like the quarks. We have the up and down quarks and strange quarks and the anti-quarks. And from the story, the reason physicists were able to figure out that there are quarks was actually because of mathematical symmetries and groups. And it was hypothesized by the mathematicians long before physicists were actually able to even prove it, which makes sense, and I think this happens a lot, particularly in physics. I don't know about all of science. I don't know if the same thing happens with like biology or chemistry, but physics for sure. And I was actually also interested in physics before I was ever interested in math. I absolutely hated math in high school, and I hated it up until my calculus class in high school. And then I still didn't particularly like it. And then I learned that it's not about memorization, it's all about understanding and playing in art, and then I loved it. But point being is that I used to love physics first because I was curious about it, and I had started to read this book that explained time and general relativity and quantum mechanics. And the way I would always explain it to anyone who asked me is that I think physics is the magic that adults say isn't real, because in physics, things can pass through walls. Time can slow down and speed up. Something can be in two places at the same time or be in two different states at the same time. And in fact, it is. Light is. Light is both a particle and a wave, always, all the time. It's all these things that like adults say like, oh, that's magic, or that's not real, that doesn't happen in real life. And you know what? It does. It really does. Particles can pass through walls. It can happen, right? And like superposition, which is the whole light thing that I just told you. Anyway, it's so cool. It's really, really, really cool. Maybe if I remember more of it, I can talk more about that as well. I think I'm more into physics. I think I'm more into math now than physics, but it did definitely start with physics. So that's where we're at. Anyway, I didn't actually do that much more reading or exploration this week, so we're going to stop there because I kind of just ended up going on a rant about things that I remembered, and maybe that would be fun to do at some point. Just like sit down and be like, here's a class. What do I remember about this? Or what can I figure out from the things I remember, like angles, trigonometry, algebra, geometry. Ooh, geometry and taxicab geometry. That is fun. And like all the different geometries. Geometry is fun because you can take the same like postulates, Euclid's postulates, right? And you put them into different geometries of things, which is like the regular geometry plane, but then the spherical versus taxicab geometry. Anyway, I gotta go because I gotta go talk to someone, which is my friend. So I'm gonna stop talking right now. Hope you enjoyed, I don't know, hanging out, talking about math. There's lots of cool people in these comments now, so I hope y'all connect and like, I don't know, talk about some of these things. What are you curious about? What are you learning about that you find particularly interesting, or just what are you hoping to learn more of? Particularly the questions. Let us encourage everyone together to ask more questions and hopefully guide themselves and each other in our curiosities and encourage that. So cool. Anyway, gotta go. See ya. Bye.